Hey guys, I'm back. So once again, I'm at the farm. We're going to kind of pick up where we left off yesterday. Actually, I left the formulas up on the board. So we left off with yesterday with the power formula, where power equals work divided by time, or the exploded version, power equals distance times force divided by time. So now let me just kind of read verbatim the intro to the chapter on torque. So torque can be visualized as a twisting effect. Okay, so keep that in mind. Torque is always twisting. Not necessarily moving, but always twisting. And that'll make a little bit more sense in a minute. Does not necessarily imply or require motion. For example, we use the term torque a bolt to mean we've applied a sufficient amount of torque to a bolt to adequately secure it. Once the bolt is set, it does not move. So just like the lug nuts on your car, or if any of you gearheads out there, it's very important that you torque down your head bolts to a certain spec, a certain level of torque. You don't want to have them too low of torque because it won't seal properly. You don't have too much torque because then it can break the head bolts, and that's a really bad thing. But just like those nuts on your wheels of your car or on the head bolts, they're not moving. If they're moving, you've got big problems. That means your wheel's falling off or your engine's coming apart going down the road. So once the bolt is set, it does not move. Torque was applied to the bolt to secure it. If a wrench is used to remove the bolt, an inadequate torque is applied to the bolt via the wrench, the bolt will not turn. So to kind of give you an example of what torque is and how it works, think about that. If I tighten a bolt to 100, we'll just use an arbitrary number, no denotion to it, no units, just I torque it to a level of 100. Well, if I try to take that bolt off and my son, who's 6 years old, tries to take it off and he can only push to a level of 50, he's not going to get that bolt off. It's been torqued to 100, so 50 is inadequate to take it off. In much the same way, if he torques a bolt down to 50 and I push with a force of 100 units, for right now, then I will take the bolt off. I have enough power to do that. And that's kind of the idea of torquing your bolts down. You want to tighten your lug nuts on your wheels of your car to a certain force where they're not going to back off on their own. They're held in place by that torque. They're not moving, as a matter of fact. So in this case, torque may be applied, but may be inadequate to the bolt move. So first thing, let's just go ahead and put the equation up so that we can get kind of some context of what we're talking about. I'll zoom in on this in just a second. Make sure I got my notation right. So our equation is TO equals F times LA. Let me rewrite that A a little better. LA. So for those of you in my class, some of this probably seems a little familiar. TO obviously stands for torque. We're solving for torque. F, like in many of the other equations in the past chapter, is going to stand for force. And LA, if you remember back to chapter 2, yeah, I believe it was, we talked about simple machines and leverage and class 1, 2, and 3 levers. LA means lever arm. So what this equation stands for, torque equals the force times lever arm. So applicably what this means is we have a lever arm and we push force at a certain length, which is our lever arm, and that gives us a torque. Okay, so what do I mean by that? Well, I've got a little something set up over here. So once again, we have the 3430 Ford, fantastic little tractor. Now I'm going to get down here where the lug nuts are. And if you'll see, I have this, some people call it a bolt breaker. It's got a kind of a couple different names. Around here we call it a pull handle. I don't know where that came from. And basically we have these lug nuts and they're so tight. Well, if I push out here, see if I can get my angles right, I'm applying force, say, at this very point. Now, I've already measured this. See if I can do this with one hand. From where the force is applied at the end of the lever to the center of the pivot, which is the middle of the bolt, right there, the point that everything revolves around, is 21 inches. So if I push, say, right here on the end of it with, I don't know, I'm just making up a number, say I'm pushing with 100 pounds, and I broke the bolt loose. So now I can take the bolt off, Once it's broke, it takes very little torque. There's not a lot of resistance against it. So this is tight, right? No, that's not tight. I did that with my hand. So to make this tight, we're going to apply torque to it. So we want to torque this bolt down. So I'm going to grab out here a pre-measured distance at 21 inches. And I'm going to pull up. I'm going to apply, like I said, I don't have a scale with me or anything like that, but I'm going to say, for example purposes, I'm pushing with 100 pounds of force at 21 inches. All right, how much torque did I just come up with? Well, let's go back over here to our board and let's calculate this and figure it out. So we plug this in. How much torque did I just apply to that bolt? We're going to say, to use our equation, TO equals F times LA. We'll say what I estimated I pushed with about 100 pounds of torque times, what was our lever arm? Well, we measured it. It's 21 inches. 21 inches. So what is 100 times 21? TO equals 100 times 21. Don't have to rewrite it. 2100. Now what's our units? Just like in the work formula, where it's distance times force, this is force times length. So it's going to be the exact opposite. Remember where I said we write these equations in such a certain way. So torque could be LA times F. The mathematics will work out the same, but we're going to keep it with F times LA to help us with our notation. So force, that's our weight. And length arm, in this case, is in inches. 2 marks equals inches. 1 mark equals feet. So inches. So I just torqued that bolt to 2,100 pound-inches of torque. That's how you would say that. Now, you may be thinking to yourself, you've heard this word torque. Where I hear most people coming from it, where I hear this most talked about are like truck commercials usually. 3/4 ton Ford, Chevy, Dodge. It has 500 pound-feet of torque. Actually, they typically say foot-pounds of torque, which technically they're wrong. They're saying it in work terms. So I apologize if I'm going to mess up that notation later. It's ingrained in everybody's head to be that, but the technical term is the force before the length. So this is pound inches, but most of the time when we hear it, it's foot pounds, right? So simple conversion, right? So 21 inches. If we want to have this in foot pounds, we could go back and convert this 21 inches. So how many feet is in 21 inches? So very, very simple math. Like all of this, 21 divided by 12 equals 1.75. Is that right? Yeah, that's right. So if we were to go back and erase this, and instead of 21 inches, we use 1.75 feet. So we end up with 100 times 1.75. And that gives us 175 pound-feet. Oh, almost messed it up. Pound-feet of torque. That's more common to what you're used to. So what does that actually mean? When they say a truck has 500 foot-pounds of torque. Sorry, said it backwards. I told you I'd mess up. Pound-feet of torque. What does that actually mean? Well, if you think back to our earlier chapters on leverage again, we know that a circle like this wheel right here is nothing but a continuous lever. So if we were to take this and get a cutting torch, or imagine we took a picture and erased it, and we erased everything except this section going up and down, we would have a lever. It's just a whole lot of levers really close together. So this particular wheel, I'm just estimating here, it's about 24 inches. We'll say 24 inches for easy measurement. Well, if we were to take this tractor and put a jack under it and lift this tire off the ground, and we were to, I don't know, wrap imagine, just bear with me for a minute, crazy example, and we were to take and wrap a tow strap or a chain around this tire, and we say we want to connect it to that tree over there, and we want to pull that tree over. We jack this tree up. We basically turn this tire into a winch. where it is pulling at this outermost point, what we essentially have is we have twisting power, which is by definition torque, and we have a lever arm that is 2 feet. So let's go back over to our board for a minute. If we were to take this, and so how much torque is applied? TO equals, let's say we do that and somehow we measure that chain pulling against from the tire to the tree. And it's, I don't know, 1,000 pounds. And we know that that lever arm, the center, so draw a little picture here, from the center of the tire to where the chain is, this is 2 feet. That is our lever arm. So 1,000 times 2, simple math, we end up with 2,000 pound-feet of torque. So why is that? What that is it's the equivalent to, if we were to take this, wheel, that means at this point, it's pivoting around the center here. At this point, it's pushing, pulling, applying force, however you want to imagine it, at 2,000 pounds. So it's 2,000 pounds at 2 feet. No, I said that backwards. It's 1,000 pounds at 2 feet. If we were to take the tire off, and this has what's called a spin out wheel. If we were to shorten this down to where this and put it, say, a 12-inch wheel on it, it would pull at 2,000 pounds at 1 foot. Okay? So it's a ratio. It's 1,000 pounds at 2 feet, 1,000 pounds at 2 feet, 2,000 pounds at 1 foot. If we were to put a really big tire on this, we would only pull, what would that work out to? 333 pounds at 3 feet. 660, I'm sorry, math's wrong in my head. 660 pounds at 3 feet, 500 pounds at 4 feet. It's all the same amount of torque. The power at this center point is all the same. It's 1,000, 2,000 at 1 foot, 1,000 at 2 feet, so on and so forth. So that's how torque is applied. We use torque in a couple different ways. So once, obviously, the power. So when you hear in the truck commercials, that's actually what they're measuring, is the spinning power of that back wheel to come up with the torque. That's how most of the time we think of it, but it can also be used to calculate a type of horsepower, which we're going to get into in the next video. Tractors have 2 different types of power, 2 different types of horsepower. It's measured at 2 different points, and they're very similar, but they're usually a little different due to some friction, some loss of power along the way. But like I said, we're going to get into that in the next video, and I will see you guys later.